Okay, let's start our lecture number 23. That's our penultimate lecture. The next lecture is going to be the last one to close this course. Today we are going to we're going to look into a simple model to describe the response of material media in general, right? This model can serve to explain several features that we observe in the interaction of electromagnetic waves with material media. For instance, it can explain, for instance, the transparency of certain materials to electromagnetic radiation. For instance, glass, right? Glass allows light to go through in the visible range. It explains, for instance, why certain materials are opaque to the passage of electromagnetic radiation. Metals, for instance, why do they reflect? Why an electromagnetic wave bounces back when it reaches a metal surface, right? So these are general features that this model, which is called the classical harmonic oscillator model, can explain. So we're going to review that. We're going to start with a simple model for just one charge that oscillates on the application of an external field. Then we are going to generalize, so I can really describe with this generalized model the permittivity function, and why we observe those absorption bands along the spectrum, electromagnetic spectrum, in different materials. So that's essentially what we're going to show, and also the nature of this permittivity function. This concept can be also extended to the permeability function. Similar behaviors are expected to occur in certain frequency ranges. So the type of phenomena we observe when we talk about permittivity are similar to those when we talk about permeability. Okay, so that's why it's important to consider this as a model that can explain different parameters. And finally, we are going to talk about Poynting's theorem for linear, homogeneous, and isotropic media in the harmonic regime. The reference for this lecture are my ebook on chapter 7, we talk about that, and also Jackson's classical electrodynamics, sections 6.9, 7.1, and 7.5. Well, the classical electron oscillator model, in fact, we already did some partial introduction of this model. We spoke about the Drude model when you have free carriers in a conductor subject to an external electric field. We talk about that in the static regime or in the stationary regime. Now we want to talk about a situation in which you have, for instance, a simple atom with one nucleus, let's say, a positive nucleus, just one electron. Let's say hydrogen atom, or a simple dipole, right? Any type of situation. It can be an atom, it can be a dipole, a pair of charges responding to an applied field. What we have here is that, let's talk about atoms, so we talk about the materials. We have some important parameters. We have the electron mass, which is the, which is the element we want to focus our attention. The electron charge minus Q, so Q is a positive number in this model. The electron position vector, which is a curly X. In fact, I should emphasize that curliness I put a round thing here. So there's a vector, a capital X, curly capital X. Okay. So we know that we have already done that before. When you have an electron cloud, okay, let's just draw here. Electron cloud. Oops, let me just do like this. This is an electron cloud. You have a nucleus. Let's look into this. So at the center, you have some positive nucleus. So let's say that the electron is distributed according to the wave function of the atom, right? So we have a probability function. Let's use that probability function to define the charge density of the electron. So I have a minus q coulombs that are spread around a spherical region of radius a, right? If we displace that, because we apply an external field, if we displace the charge center, the positive charge center relative to the negative charge center, so now we are going to have the position is a new one, right? So the position, the plus charge went to this new position here. So now it is on a region that has a certain distance, let's say r. So assume that we don't distort the electron cloud. So we have a uniform density here. Let's say that this is on a medium. So we have the atom. So we have vacuum, right? All around. So we know from Gauss's law that the field on the positive charge, right? Remove the positive charge. Just calculate the field due to the electron charge. We know, because we showed that before, that the field is radial, which is the density R divided by 3 epsilon 0. Let's say that R equals to D. So that's the displacement D, right? So the field is rho D divided by 3 epsilon 0. So that's the force on the positive charge by the principle of action and reaction. We have an equivalent center for this negative charge in the center. We have an opposite force of the proton or the nucleus on the charge center, which is in the opposite direction. Let's look at the force in the positive charge. So this equals to force per unit charge, right? There's the E field on the proton, on the positive charge. So the force equals to density times, you can write like this. Density, electron density, which is, I'm using only a magnitude, calculation here, okay? I'm not going to put the sign because it's not important. The density is a charge of the electron divided by, it's minus that, right? But it's the magnitude divided by 4/3 of pi a0 cubed, or if you want, is a wave function defined for the hydrogen atom, let's say, okay? But assuming that is a uniform density, that's what it is. So the force on the positive charge is going to be rho Q. Rho Q is this relation, so it's going to be a Q square and a radius, etc., right? Divided by 3 epsilon 0 times D. Okay? So we have an attractive force which is proportional to the displacement. So you see that when you have a departure from the charge center, you have a neutral atom, neutral, right? You displace the charge centers, there's a restoring force, which is proportional to the displacements. So that's what we have in our model here. The force acting on the electron, let's assume that our reference is the nucleus, okay? Our reference frame, the origin is at the nucleus, so have the electron departing from the nucleus. We are going to have a restoring force which is proportional to the displacement, right? So we are going to have this type of force which is attractive, which is something like this, minus k times the departure of the position vectors relative to the equilibrium position, which is at the origin, right? So we can, we can relate this to elastic force and define a resonance frequency omega 0. We can say that k, the elastic constant, we are calling elastic constant, but you see that the origin is exactly this model I just showed you, that the force, a Coulomb force, is attractive in this sense, and is proportional to displacement. So you see that the elastic constant equals to, we are using this parameter, but we are going to use k also for wave number. But the elastic constant is m resonance frequency squared. Okay, we call this the resonance angular frequency, omega 0. You can look at the SI units. You're going to see that they compare. So we have when we have an E field and we have the nucleus, attracting the electron, we have this force, which is elastic force, which is due to that Gauss's law I just showed you. You have an electric force on the electron, which is the charge of the electron minus Q times E. And also we have some force that gives some damping to the system. As the electron tries to oscillate on the application of an oscillating field, for instance, it's going to interact with the surroundings, right? So every time we have some interaction, we have some energy loss, we can always model that with a viscous force, which is proportional to the velocity. We did that in our Drude model. When we talk about conductivity, we show that due to collision of electrons when they move around in a conductor, that collision that would be characterized by a collision time, it was characterized by the fact that the starting value of an average velocity of electrons in a conductor would die away to 0 in a collision time, typically Tc, okay? So the velocity would go like this, with 0 exponential minus t over Tc. And we showed that if we work this equation, we can show that this is equivalent to the system having a viscous force proportional to the velocity and against the motion, right? So that's what we have. We have a viscous force, Fv, proportional. We're just putting here the dimension. I'm putting a mass, okay, damping constant, and which is called the damping frequency, times the velocity, which is x dot, time derivative, right? X dot here means dx dt. We're going to use this terminology here, this symbology here. So this implies that, in fact, this damping frequency, let's say, which is has a dimension of t to the minus 1, is the inverse of the collision time we spoke about in our Drude model for the conductivity, right? So we have, in addition to the elastic force, which is proportional to the displacement and the pulling back the electron, we also have this visceral force, which means losses proportional to the velocity. So we have restoring force, electric force, and dumping viscous force. So Newton's law, Newton's second law, establishes that the sum of forces on the electron, let's assume that the nucleus is the reference. We're not looking into the nucleus, we are going to do that when we generalize the concept. Let's just look at the electron. So I have the force m times acceleration equals to the sum of the applied force, which is electric force, plus viscous force, plus restoring force. Let's assume that X has 3 components, okay? X, Y, and Z. In fact, those are curly. Let me just improve this thing here, according to our notation here. These are curly symbols because they are rounded symbols, because we are talking about time-varying quantities. So we have this X, curly like this, Y, like this, and Z is like this. I'm putting this rounding thing here just to remind you that this is a different symbol, you know, not exactly the symbol traditional X, Y, and Z, which are going to be used for different regime, okay? The E field. So X has 3 components in Cartesian component and in rectangular coordinates. Let's assume that the E field is applied to one direction. The system is isotropic and linear, okay? So we don't have any nonlinearity here. So what we have? We have 3. We can break down this vector equation into 3 equations. Second derivative of the x coordinates, gamma times the x coordinate, because it goes to the first left hand side, right? Omega 0 square. Then we divide everything by m. Then we have minus q over m times e. That's for the x direction, right? We have some non-homogeneous differential equation. And to the other directions, the only difference is that we don't have any applied field either in the y or in the z direction. Okay? Let's look into those equations, those homogeneous equations, quickly here. So we have something like this, right? Let's call it f. The equation is something like this. It's a second derivative of a function plus gamma times f dot plus omega 0 squared times f equals 0. We know that the type of equation is has a solution of the type, let's say that's lambda t, right? Let's try that. So f dot is lambda exponential, and f double dot is lambda square exponential. Let's try for this solution, see if it works. So we have a characteristic polynomial, right? So we have you know, some replicas of f, the derivatives, right? So we're going to have lambda square plus gamma lambda plus omega 0 square lambda times f equals 0, because f is lambda t, and we have the characteristic polynomial, and we can find the roots. We have 2 roots. It means that we have 2 independent solutions. So let's do that. Minus gamma plus or minus gamma square minus, right, 4 times omega 0 square over 2, and we can still do a little more here, minus gamma over 2, let's see, yeah, that's what we have, plus or minus, I'm going to put the 2 inside, gamma over 2 square minus omega 0 square, right? We are interested in the regime in which the resonance frequency is larger than gamma over 2, or in general, that's what's going to happen is that omega 0 might be much larger in low loss systems, okay? So this is loss, right? Damping. If the damping is small, this is expected to be small relative to omega 0. Might not be sometimes, right? But it's going to be in general. So assuming that omega 0 is larger than gamma over 2, we see that this number is negative. Then we have a complex number coming out. So we have lambda equals to minus gamma over 2 plus or minus j times a frequency omega, which is, by definition, the root square of changing the position, right? So omega 0 square minus gamma over 2 square, which is a positive number. So we have this is called, in fact, the natural frequency. Okay, natural frequency because it's going to be the natural oscillating frequency when if you simulate an oscillating system and you turn off the source, you let the system oscillate, it's going to oscillate in the natural frequency. That's what happens. The fact is that the natural frequency is very close to the resonance frequency for small damping, right? But what happens here? The solution is on the form f equals to exponential of minus gamma over 2 times t, exponential plus or minus j omega t, and we can combine those to generate sine and cosine functions. So the solutions are either exponential of minus gamma t over 2. I mean, I can write like this. It's going to be sine and cosine, right? Or I can write in general, solution is something like this. I can put an amplitude as well, right? An amplitude exponential of minus gamma t over 2. Then you have a cosine of the natural frequency t plus a phase. You can do that because this is a combination of sine and cosine. So that's, I mean, in the directions y and z, we don't have any applied field. What happens? That's the general solution. Behavior of y and z is something like this. It means that if for some reason you had an initial condition with y and z not equals to 0, right? Not equal to 0. Then they will die away, they will damp down according to this behavior, right? They are going to oscillate if you don't have any stimuli. They are going to oscillate with the natural frequency and going to damp, going to die away with the time constant, which is 1 over gamma approximately. Right? I have a 2 here, but just to give an order of magnitude. So inverse of gamma is 2 over gamma is a characteristic time, right? So that's what you have. Well, what happens in the x direction depends on what type of field you apply. For a given time varying field, the system is going to respond, let's say, with a mix of the time variation of the field and the natural time variation that is that due to the natural frequency, let's say. Okay. If we apply an oscillating field with a given frequency, we turn on the field, so the system in the x direction, let's say, is going to go to a transient behavior with a mix of oscillation between natural frequency and applied frequency. And after a long time, the frequency reaches what we call the steady state, in which it's going to oscillate in the frequency of the applied field. So if you do a steady state analysis, let's assume that at steady state, the E field is harmonic with frequency omega. Can define that in terms of a phasor, which is straight E now, round E or curly E, and straight E, exponential j omega t, right? So in the steady state, as I mentioned, x is going to oscillate in the same frequency, omega. So x can be written now. You see, there's a difference between. It's a very subtle difference, you know. This is a curly x. It's real part of the traditional x that we use, which is there's no special, you know, rounding in it. So the real part of x exponential j omega t. So this is a phasor x. This is a time varying function x. This is just a phasor in the complex domain, right? So when you do that, if we calculate, let's look into the equation, right? So we have x plus gamma x dot plus omega 0 square x equals to minus q over m e, right? Now, if I make x equals to 1/2 of x exponential plus complex conjugate, which is the same thing as saying that this is equals to the real part of x exponential j omega t, and e is the same, right? And if we plug those into the equation here, we're going to have an equation for the real part, and once this equation is satisfied, we have the same result for the imaginary part. So you see that this 1/2 on both sides will be cancelled, and we have second derivative is j omega square, right? Plus j omega gamma times x plus omega 0 square x, all times exponential of j omega t plus the conjugate. That's what they do, right? Divided by 2, but they cancel that out. Equals to minus q over m e exponential j omega t plus the conjugate. Okay? So it's just enough to satisfy this equation here. We just balance this term with this one, and the complex conjugate automatically will be balanced. So that's what we have. We have this algebraic equation. You see this is minus omega square, everything times x, so we have omega 0 square, which is this term, minus omega square. Then we have plus j omega gamma, right? J omega gamma times x, phasor x, equals to minus q over m times c. So we just solve for the phasor x relative to the phasor e, then we calculate the physical quantity x, curly x, right? So we have x equals to minus q over m. Then we have a function of frequency. That's E, right? Well, why are we doing that? Well, we want to determine what is the induced dipole moment in the material. Apply a field, see how the atom respond, then we determine the dipole moment, then we assemble several dipoles. we assemble the material, we assume that we have a density of dipoles, then we calculate the polarization, right? That's the step by step. Calculate the displacements, calculate the dipole moment, P, calculate the polarization, then you calculate the susceptibility, because we relate polarization with field is a susceptibility, then you go to the permittivity. Once you have susceptibility, you have the permittivity. That's a step-by-step procedure. So that's what we are doing. We are interacting the field with the charges, bound charges. Before we interact the field with free charges, right? Now we have bound charges that can have to be restored back to the equilibrium position. We go to the dipole moment, polarization, susceptibility, and permittivity. So let's calculate the dipole moments. So we have here the nucleus and the electron. Let's say that this is x plus, this is x minus, right? So the dipole moment equals to the positive charge, x plus x minus. Minus x minus, right? Why is the minus? Because it's q times x plus the negative charge, which is minus q. That's where the minus comes from, times x minus. So, which equals to p x, that's it. I don't have to do anymore. So x plus minus x minus is the vector that goes from minus to plus, right? You see that the position in the steady state is the position of the electron, right? The position of the proton or the nucleus, let's say, equals to 0. So in this case here, this is going to be, in fact, y at steady state equals to 0 and z equals to 0. So this is going to be q times x plus equals 0 minus x, 0, 0. That's the induced dipole moments at steady state, right? So P, I just have to calculate the component, the x component, which is this one here. So the x component is going to be P equals to minus Q times x. So remember that P, curly P, equals to the real part of phasor P, which is this one here, exponential j omega t, okay? So we are calculating everything in the complex domain. So P is given by that. Polarization is given by, let's assume that we have any dipoles per unit volume. So it's going to be n times P. I'm not going to put the expression right now, I'm just going to show the step by step. All in the complex domain. Dipole moments, polarization. Then you go to polarization equals to epsilon 0 susceptibility times E field, right? So we have that. So this is going to be I can calculate, right? So expressed like this, we determine chi e. So chi e equals to P over epsilon 0 epsilon 0 e. Then d equals to epsilon 0 1 plus chi e times e. Then we have the permittivity function, epsilon equals to epsilon 0 1 plus P divided by epsilon 0 e. So let's put down that in terms of the quantities we determine. You see that the polarization equals to NP, right? So dipole moment divided by epsilon 0 E. And dipole moment is minus qx. But you see that x is proportional to E, so we are going to cancel out the E field in this ratio here. Okay? So let's see how it looks like in our class notes. That's x, right? Minus P equals to Q times minus x, as I just showed you. Polarization is NP, so it's minus NQX. If we express x, it's going to be minus NQ times minus Q, which is plus Q squared, NQ squared over M times E, which defines the susceptibility, epsilon 0 QE. So we have at the same way, right? Epsilon 0 E plus P, or epsilon over epsilon 0 equals 1 plus chi. So chi, I'm saying key, but it's chi. Chi is in Portuguese. Chi is can be determined. Cancel this E here, right? So we're going to have an epsilon 0 down here. So what we have is that the function epsilon over epsilon 0 is 1 plus a parameter we call the plasma frequency squared. This is a frequency dimension, because you can see here, we can identify here by inspection. And the plasma frequency is proportional to the root square of the density of electrons or atoms or the dipoles, right? Square of the charge, electron mass, and permittivity epsilon 0. So the higher the density, this is an important parameter. Okay, we're going to talk about it, what it means. For high density of dipoles, so this frequency is very high, right? I mean, goes deep into the blue, ultraviolet, or even beyond that. So it depends on the density. So plasma frequency is an important parameter, right? So what we have here, that's the permittivity function. The first thing that we observe is that the permittivity function depends on the frequency. That's very important. That's what we call the fact that this is a dispersive medium. The permittivity, which is a parameter that we are going to see that determines the speed of light in the medium, for instance, depends on the frequency. Different frequency components will travel at different velocity because of that, because of the frequency dependence. That's very important. And also we have some complex nature here, right? So what does it mean? What does it mean? What is the meaning of having, for instance, a real part of the complex permittivity and an imaginary part? Well, we are going to see that in the context of Poynting's theorem. What does it mean? Okay, what's the meaning of that? So it's very important to understand the fact that the permittivity depends on frequency. This is the same as I mentioned, right? I mean, the permittivity is a material parameter for a linear homogeneous isotropic material, which relates the electric quantities, right? If we are talking about the magnetic quantities, the parameter that defines those is the permeability. Permeability is going to be a similar behavior. Might be a type of structure like this one, you know, have this type of thing in the denominator. Behavior is similar. So it's going to be also permeability might be a complex function, and dependent on the frequency as well. So it's very important to understand that the phasors P and E or D and E, they are all proportional, right? I just showed you that. P is a parameter times E, right? The same thing, D is a factor times E. So we can talk about linearity in the, in multiplying one parameter times the field, you get the other parameter. So have some sort of linearity. P and E, D and P, D and E, phasors are linearly related. On the other hand, one cannot say that when you talk about the physical quantities in the time domain, P, D, and E, they are not, they are not linearly related. Why? Well, because this is complex number. It means that they are not in phase, right? In principle. P is not in phase with E, D is not in phase with E, so they are not the same time variations exactly. They are similar, but not exactly a multiples of one relative to the other. So that's very important. We don't have a linearly, I cannot say like this. I can say D, straight D equals to epsilon E. I cannot say that D equals something like this, an epsilon effective, let's say, times E, because we don't have this parameter in the time domain, right? This is a complex parameter, so D and E are not related by that. We might have E like cosine omega t, and D a cosine omega t plus a phase. And I cannot say that these are proportional. They are different, right? These functions are not in phase. They are not, one is not the replica of the other one. The other one is going to be the phase like this. They are similar, but they are not the same, right? So the ratio changes as a function of time. I cannot establish a linearity relation, nor I can talk about the permittivity in time domain, only if we don't have the phasing. If we don't have any phase lag, then we have a permittivity in the time domain, then we can talk about it, okay? Very important. Some remarks on the permittivity function, which is our main focus here. First is what we call the resonance condition. When the frequency of the applied frequency matches the resonance frequency of the system, you see that according to our model, the resonance frequency is something intrinsic to the system. We can determine that, for instance, we saw that constant, we didn't elaborate much, but the constant proportionality is right here, I think, right? Some here. The constant is this parameter here. Here we have the density, which has the size of the atom, let's say. Okay, this is a parameter that determines the wave function. So it has some, it has some properties here. We have some parameters there. So the resonance frequency is something that depends on the structure of the atom. So so in the resonance condition, the curious fact is that the polarization is this factor here is purely imaginary number times the E field. So it means that in terms of phase lagging, P and E have a phase lag of pi over 2. Right? This has a physical meaning, in fact. Recall that P is the coordinate. P is proportional to the dipole moment, which is proportional to the displacement of the electron. So it means that when field is maximum, right? The displacement is minimum, is 0, let's say. So it means that we always apply if we apply the field, the resonance occurs when the applied field is at the point of maximum velocity, let's say, of the electron, right? So that's the meaning of that. And the permittivity is going to be, the relative permittivity is going to be 1 minus this number here, divided by epsilon 0, which is the susceptibility. It's going to be this number here, right? Also, so if we are far away from the resonance condition, so if I have a frequency which is very low or very high relative to the resonance frequency, in other words, when this magnitude is much larger than the damping frequency, we can look into the expression, right? So let's look into that. The permittivity is this, epsilon equals to 1 plus omega p square, omega 0 square minus omega square plus gamma over 2 square, right? Yeah, that's the function. It's a very simple function. So when this is much larger than gamma, right? So so when this difference is much larger in magnitude, plus or minus. So when the magnitude of omega 0 square minus omega 0 square much larger than gamma over 2 square. Or in other words, if we have omega minus omega 0 much larger than gamma over 2, right? Then we can drop this thing here, and you're going to have this approximately 1 plus omega p square I think there's a missing J here. Let me see. Yeah, this is wrong here. This is not that. Plus J omega gamma is not gamma over 2, right? So so in this regime here, much larger than gamma square. That's what I want, okay? When this is much larger than gamma, what is this? This is, what is that? This is omega 0 minus omega, omega 0 plus omega, magnitude much larger than omega gamma. Well, I can drop this in here, right? You get something like this. So magnitude of omega 0 minus omega much larger than gamma. So we have this result here. Okay? So what we have? Well, this is a real number, right? So that's what we have. So the relative permittivity is purely real number. So it means now that in the time domain, if fields and D are proportional, P and E are proportional, then we can say that. We can talk about the permittivity in the time domain also, right? We have a real number now. So for omega smaller than the resonance frequency, below the resonance condition, epsilon relative is larger than 1. That's traditionally expected, right? But however, for omega larger than omega 0, this number is in general for insulator is smaller than 1. Okay, so so this is going to be a number. This is smaller than in magnitude is smaller than 1, this is going to be a negative number. So it means that the relative permittivity is smaller than 1. And this is an unusual behavior. So that's why we call this region, when we pass a resonance, this is called the region of anomalous dispersion, right? So that's the region when the relative permittivity is smaller than 1. So we are going to see that the velocity is proportional. I mean, when the permittivity is smaller, the velocity is proportional to, for a low loss system, to the ratio epsilon divided by epsilon 0. So when this relative number here is smaller than 1, means that the velocity, phase velocity of propagation is larger than c. And that's the next class. We're going to talk about that. And also, we have some crazy implications, okay? But there's no violation of the special relativity of Einstein's special relativity, in which maximum velocity of transport of information is always c. It cannot be larger than c. So even though we have the things here, but these are artifacts. Okay, information is always going to travel with velocity below c. So, but just to mention, that's called anomalous because of that. We have what we call, which is very frequently used, the Lorentzian approximation. Okay. So, we're going to define the ratio, relative permittivity, as having a real part epsilon prime and an imaginary minus epsilon 2 prime. We are going to see that this number here is positive. So both numbers are positive for passive medium, right? That's what we are talking about, passive media. So I'm putting a sign here just to remember that for a passive medium, this has always this form in which epsilon 2 prime is positive. So the imaginary part has to be negative. We are going to show why in a second, okay? So we can calculate in the Lorentzian approximation. Let's go back to the relative permittivity here, right? So when we are around the resonance, let's say that we have a narrow resonance, a small damping. So it means that gamma is much smaller than the resonance frequency. I'm going to break this here like this. Difference times the sum. So when we are around, let me write down here, Lorentzian approximation, which is very used in, resonating systems. So it means that omega 0 squared minus omega squared can be written as the difference times the sum. And we want to examine the behavior of the permittivity near a resonance, when the frequency is, is swept across the resonance. Then we have omega 0 is going to be very close. Sorry about that. Omega is going to be very close to omega 0. So here we maintain that. So this is going to be approximately 2 times omega 0 times the difference, right? And also in the other factor here, let's go back to the original expression here. Here we make omega approximately equals to omega 0. So then we're going to have epsilon relative is approximately 1 plus omega p square 1 divided by, then this term here is going to become that. And the other term is going to be j omega, which is omega 0 times gamma. Okay? And this is going to be 1 plus. Then we have omega 0 coming out, 2 omega 0 in factored out. So I put that in, as a factor here, plus j gamma over 2. Then I can determine the real imaginary part of this. 1 plus. Then I multiply by the conjugate and divide by the conjugate. So it's going to be omega 0 minus omega. Then you see that minus j gamma over 2 divided by square. I'm going to put, I can put like this, omega 0 minus omega square plus gamma over 2 squared. Then we have the real parts. So recall that we defined epsilon prime minus j epsilon 2 prime. So the real part is going to be approximately, okay? If I miss that, I mean it's approximately 1 plus omega p squared divided by 2 omega 0 and the epsilon 2 prime approximately. You see that the minus is already here, so it's just omega p squared divided by 2 omega 0. Then we have a gamma over 2 then we have that. The real and the imaginary parts are determined like this. That's the Lorentzian approximation. We have these final relations here, okay? Well, we can now examine the behavior. Before we show the plot, let's just talk about the general features of these functions. Let's talk about the real part. Now, the real part, as I mentioned to you, is going to determine the velocity of propagation in the medium at a given frequency for a given frequency component. And it's important to determine how this varies with frequency, right? So on resonance, this is 0, no contribution. On resonance, the relative permittivity is equals to 1. So it's like there's no material, right? A single frequency is going to propagate as if it was in vacuum, as if the medium was vacuum, right? For frequency smaller than the resonance frequency, we have an increase of the permittivity relative to 1. It's larger than 1. If we go beyond the resonance frequency, have the anomalous dispersion. Permittivity is going to be negative. 1 minus something here, right? And the imaginary part, on the other hand, has this behavior. Notice that the imaginary part has a peak when the frequency equals to the resonance frequency here. Maximum value of the permittivity is going to be reached, okay? And also, when you go to, if the frequency is departed from the resonance frequency by gamma over 2 on either side, so this becomes gamma over 2. If the difference is plus or minus gamma over 2, so this is going to be 2 times the square. So it's going to be half of the maximum value. So the permittivity falls down to half of the peak value, right? That's what happens. Also, if you go far away from the resonance, for instance, omega much larger than the resonance frequency, this goes to zero. No damping effect. Damping. I mean, if the gamma is the damping parameter, if gamma was zero, there was no imaginary parts. So this is loss. This is going to be some representation of the losses in the material. Okay, here. So far away from resonance, I mean, the interaction is negligible. There's no interaction with the dipole. Permittivity equals to 1. The field just passes without interaction. The field only interacts strongly with the material when the frequency approaches the resonance frequency. Okay? So what we have, I mean, this is the behavior of the permittivity function. Let's look at the real part. Okay, the real part has, equals to 1 here. Right? So it has a peak. Right there, right here, and has a minimum, has a peak and a minimum, and this peak takes place when you depart from the resonance frequency by gamma over 2. This, I mean, if you look at the position of this peak derivative here, the peak imaginary part is going to be exactly in gamma over 2. It's very easy to show that, right? So epsilon 2 prime has a peak value, either lower or higher, when we depart from the resonance frequency by gamma over 2. So this distance here is gamma over 2. Right? And on the other hand, the imaginary part, which is minus this, but this is the number that we're talking about, is positive, is going to have a peak value on resonance, then it's going to be negligible away. This width in which the imaginary part falls down to half of the maximum value, the width of this resonance curve, or this Lorentzian curve, this is called the Lorentzian curve, the width is gamma. The less is this parameter, the sharper is going to be the resonance effect. So this is called the full width at half maximum. Full width. This is a traditional acronym used when we talk about resonating systems. FWHM, right? Full width at half maximum. We also use this other one, HWHM, which is half width at half maximum. So in this case, gamma over 2 is the HWHM, and gamma is the FWHM of this resonance curve. Okay, that's the behavior. So we see that, I mean, when you move away with frequencies far away from the resonance, you don't have interaction, no effect. So some sort of energy is going to be stolen from the electromagnetic field, and we are going to see that in a moment. Okay. Very well. Let's now generalize this behavior, and we are going to use our concepts of dipole moment that we defined previously. Okay. Let's assume now that we have a more complex atom with several electrons. Okay. One heavy nucleus. The nucleus has protons and neutrons, right? Neutrons have no charge, but they have a mass. Mass is very important. So the nucleus has a mass m. Okay. Let's say you have an atom with atomic number Z, right? We have Z electrons, and you have Z protons, and you have something like Z neutrons. So it depends on the atomic mass of the atom and the atomic number Z, right? We cannot say that exactly, but sometimes it is. Most of the time it is. Number of neutrons, number of protons are equal approximately. So we have two Z entities like this, and Z electrons. But recall that the mass of the neutron is approximately equal to the mass of the proton. So let's say that we have, if the electron mass is m, and the proton mass is p, so we have a total mass of electrons Z times me, and the total mass of proton approximately, because proton is nucleus, is 2 times Z mp, right? But the proton has a mass which is 1840 times the electron mass, right? So you see that even a heavy atom with several electrons, Z times m electron is not equal to the mass of the nucleus. That's the mass of the nucleus, and you have Z times mass of the electron. So this quantity is very small, and this consideration is going to be important when we make some analysis on the model of many charges. So just to situate you, so the nucleus has a mass m, total charge zq, right? Z is the atomic number. Let's say that has a damping constant, damping frequency gamma 0, and a resonance frequency omega 0 now. And we have several electrons with different properties. They have the same mass, they have the same charge, minus q, but they have different damping constants and different resonance frequencies. Let's assume again a field is applied in the x direction. So we have a neutral atom here, right? So let's see how is the permittivity function in this case. So let's just review what are the parameters that we have. For the nucleus, the mass, let's label I equals 0. M0 is capital M. For electrons, I goes from 1 to Z. Mi equals to m. The charge of the nucleus is Z times the charge of the proton, or the electron. The charge of the electron is minus q. Damping constants, we are going to label gamma 0 for the nucleus, gamma I for the electrons. I goes from 1 to Z, right? Resonance frequency omega 0 and omega I. Position vector, now let's be careful here, okay? Everybody can oscillate, including the nucleus. The nucleus difficulty is going to be taken into account now in our model to determine the generalized permittivity function. You see that the position vector is going to be this capital curly Y here, because I want to differentiate from the equilibrium position for the nucleus. X equilibrium 0 is going to be just label x0 here, okay? This is straight x0 plus the curly x, which is a variable, is the displacement of the nucleus relative to the equilibrium position. For the electron, the location time varying vector position vector y, curly y, I, right, equals to the equilibrium position plus the displacement xi. Okay? So these are equilibrium values, x0 and xi. Straight letters, right? So these are departure from the equilibrium position, x0 and xi. Okay? So the dipole moment, let's look into that, because the dipole moment is required to determine polarization and then to determine the permittivity function. The dipole moment, curly p, equals to, that's the original definition we derived in our analysis, is sum in all charges of the atom now. Okay, we are taking into account the nucleus too. We didn't do that in the previous model, right? We're just looking to the electron. Let's see what happens when we have the nucleus. So we have a Qi times location of the ith electron. at equilibrium, P equals to 0 because there's no dipole moment. This is, a linear system. Polarization goes to 0 when you remove the field. So if we write down y is going to be the equilibrium position for each charge in the system. So we have that combination equals to 0, and we can separate the charge in the nucleus, which is ZQ, equilibrium position of the nucleus, plus we sum over the electrons, which charge is minus Q times Xi. So what do we show? We show that X0, the equilibrium position for the nucleus, is that average value relative to the equilibrium position of the electrons. Okay, this is very important for us to determine the dipole moments when we apply the field. Let's assume that again we apply a field in the x direction. So we go to the ith charge, including the nucleus charge. So what we have, the differential equation is very similar, right? Newton's second law, mass times variation in the position vector of the ith charge equals to the Qi times E now, right? Qi is going to be positive for the nucleus, negative for the electrons. Then we have the viscous force, right? Has to do with the time variation of the vector position. And we have elastic force, but we have to be careful. Elastic force is something that is related to the displacement, right, of the ith charge. The displacement, the restoring force, is relative to the displacement from equilibrium position. So it's the absolute value minus the equilibrium value. That's the displacement. That's how you calculate this restoring force. Right? But notice that the derivatives of the absolute quantity, second derivative equals to the second derivative of the absolute value of the relative position vector, because the equilibrium position has 0 time derivative. Same thing for the first derivative, and yi minus x equilibrium I equals to the relative displacement. So the differential equation can be written entirely in terms of the relative position, the relative displacement, right? So this becomes yy becomes xy double dot, right? A field xi in place of yi, and here we have the relative displacement, okay? And then we break down this in terms of the x, y, and z coordinates for each particle. Right? Let's go to the ith particle, ith charge, let's say. Curly letters here, right? So for x direction again, we have a very similar equation. You have homogeneous equation for the other directions, and we know that those go to dump down with the natural frequency of each coordinate. If you let them to be different from 0 at c equals 0, they die away, right? So we don't have to worry about them. You just have to worry about xi. Again, we assume the steady state, right? Then we have again the same result. The only difference is that xi now has those parameters, resonance frequencies and damping frequencies for the ith charge in the system. So then you go to the dipole moment, which is at steady state is going to be something like this, only one component. And the time domain dipole moment is the real part of this straight P here. Right? So again, let's write down the x position that we have to use is Qi times equilibrium plus this is in the complex domain already, right? Equilibrium plus xi. Then you can separate this term here. We showed before that this is 0, right? Show that this is 0 because at equilibrium, the DC value is 0. There's no steady state. There's no constant dipole moment in the system, only a variable one. So, which is going to be due to the displacement that we calculated through the differential equations. So, so now we have this is the dipole moment. Then we can separate the nucleus contribution x0 times zq, which is the charge of the nucleus, and the electron contribution xi, I goes from 1 to z, and charge is always minus q. Then you go to the dipole moments, right? Multiply by the charge. Each I mean, we replace the coordinates, right, by that frequency-dependent function, which is right here. Where is it? Here, right? We replace that for I equals 0 and yi different than 0. Then we're going to have x0 has a zq here, right? x0 equals to q0, which is zq, m0 equals to m. Then you have omega 0 square minus omega square plus j omega gamma 0. That's x0 here. Just to show you, that's going to be zq times dZq here, right? So that's why we have zq square here. That's the contribution of the nucleus and the contribution of the electrons. It always goes with the square of the charge. It depends on that signal of the charge, right? Then you go to the polarization, it's n the density times the dipole moment, and you go to the susceptibility. Then you determine the susceptibility, contribution of the nucleus plus contribution of the electrons. Then you have the relative permittivity. We have this generalized function, okay? It's useful to use, to assume that some electrons have very similar resonance frequency, and we assume that we have k groups of electrons. Each group has similar properties. In the kth group, you have a fraction fk of electrons with similar properties, okay? So the sum of these fractions is always equals to 1, right? So the fraction times z, which is the atomic number, is the number of electrons at the kth group with the same properties. So what are those properties? Well, the properties is that they have the same resonance frequency in the given group, the same damping frequency. If you have only one electron, it's going to be only one, but it might have more electrons similar. Degenerates electrons having similar properties. Okay, so in this case, this is going to be the same term here. And here we are going to, you see that we're going to have, now the sum becomes sum between index by the group index, from k equals 1 to k equals capital K. So you have, if you see here, you have z squared divided by z, which equals to z, and z times fk, which is z squared divided by z, right? So I just show you, why I wrote like this, because z squared divided by z is z, and z times fk is the number of electrons in a given group, so that's, we clumped them together. Oh. So I wrote like this, so we have the same factor here. That's why I wrote like that. And I have mz down here to compare with the mass of the nucleus. We just spoke about that before starting the discussion, right? So I have m times the atomic number and mass of the nucleus. And here we have a factor which is the same, okay? So f is a number which is less than 1. So we have an idea. We can compare, I mean, this is less than 1, this is 1, right? So, but I mean, the sum of all of it is going to be at the most equals to 1, let's say, right? So we can compare directly those factors if we need to. So, I mean, this function now, this generalized, let's say, this is a generalized. We're not talking about plasma frequency yet. We're going to talk about it, but let's leave it like this form here. But you see that we have several frequency-dependent components which have the similar behavior that we just discussed for the single electron, right? They have that resonance, the thing that has a peak value on resonance, the imaginary part. The real part is 0 on resonance. We have this same, behavior, very similar to the single charge, single electron, let's say. So I have different regions. I mean, in fact, we have different regions here, right? We have different frequency regions, different resonances across the electromagnetic spectrum. That's the response of the material to the passage of electromagnetic field. You see that omega 0 has to do with the restoring force of the nucleus, which is heavy, right? So the nucleus has a higher inertia. So the nucleus has a low resonance frequency. So the nucleus has contributions, let's say ionic parts of a solid, heavy ions, and we have electrons which are light, right? So the heavy ions or the atoms in the material, they respond slowly, because omega 0 is proportional to the mass constant and has to do with the mass of the material, right? So the heavier the charge involved, the lower is the resonance frequency. So it means that the nucleus has some effect, but at low frequencies. You might have some, microwave response or near infrared or millimeter wave response. So if you're talking about the electrons which are lighter, their restoring forces give higher resonance frequencies, which are going to, infrared, visible, and so on. The response of electrons. So you have different regions of the electromagnetic spectrum, including those regions of the nucleus. Okay. So it's important to understand how this thing behaves. So that's what the type of spectrum we would see in an arbitrary material, right? We have resonances in which you have anomalous dispersion. You see that, for instance, here we have a very strong resonance effect. That's the real part of complex permittivity. So it goes below 1, but then you have another resonance that raises the permittivity. So the effect is a combination of the influence of different resonances. So that's what we have. If those resonances are close together, you start mixing things here. The function becomes more complicated. And also, you see those absorption bands or absorption lines, right? You might have several absorptions together like this, have regions of high absorption. I'm talking about absorption because we know that the imaginary part is related to the damping, viscous force, right? And damping means loss. So this means higher absorption, right? So you might have some isolated lines, you have very narrow spectral line absorption, atomic absorption, for instance, and you might have several resonances depending on the mix of. If you have a material that has a mix of different components, different substances, right? Like an oil has different hydrocarbons, each one with their specific absorption bands. So you have a mix of effects. So that's what the material will show you in relation to their complex permittivity. Let's look at some important. This function is useful to explain several things, including metals properties. We're going to see now. If we have a very, very high frequency, suppose that we have the maximum resonance frequency of your system is omega max. And suppose that we went well beyond that frequency. We apply a frequency that is much larger than maximum resonance frequency. So what does it mean? We're just looking into the expression here, right? So we can neglect, I mean, omega dominates the denominator here. So we're gonna, you're going to simply neglect everything that's not related to omega here. Omega squared dominates, right? So this goes away, this goes away. So we have a omega square. This sum can be calculated. I can remove omega squared from the denominator. I mean, in fact, it's this one, right? I can cross that, cross this one, and this one. So you have the sum of fk, which equals to 1, right? So I have those terms here. Let's see how it looks like at high frequencies. So you see that you're going to have a factor divided by omega square minus. And this we call the resonance frequency. So let's look into that. Omega much larger than omega p. So look into the formula here. So you're going to have this mzq square over m. Then minus 1 over omega square, right? That's the factor that we have here, right? 1 plus that. Let's see here. Let me just put like this. There's the contribution of the nucleus. 1 plus that, right? The other term is mzq square mz epsilon 0. Right? This is 1 minus omega square. So minus mzq square divided by mz epsilon 0 1 over omega square. So the relative permittivity equals to 1 approximately, right? 1 plus 1 minus 1 over omega squared. Then we have this factor here, n or in other words, well, we call this the plasma frequency, okay? Omega p squared equals to n zq squared divided by epsilon 0. Then we have 1 over the nucleus mass plus 1 divided by z times the electron mass. That's the factor that we have to compare. So what is this? M, as I mentioned before, is neutron, is 2 times, this is 2 times Z approximately mass of the proton, which is 2,000 times, mass of the proton is 2,000 times the mass of the electron. So this factor is 4,000, let's say, times smaller than this one, right? So you can neglect that, just consider this one. So the plasma frequency becomes approximately just the second term, right? mz, and it's very important to see what happens. Now we can z square divided by z equals to z. So you're going to have n times z q square divided by m epsilon 0. So the plasma frequency equals to, it's very important formula, right? N z q, I keep it like this, q square, right? Let's keep it like this, could put the Q square outside, going to be a charge. So that's what we have. For very high frequency, omega is much larger than the maximum resonance frequency. Then what do we have? Well, the response of the system is like this. 1 minus omega p square over omega square, right? This number here is smaller than 1 for insulators, okay? In fact, it's not smaller, I'm sorry. This is valid for omega very high, so omega has to be larger than omega p in this model that we're talking about here, okay? In this consideration here. So this is valid for in that regime, so it means that epsilon divided by epsilon 0 is smaller than 1 for very high frequencies. So it means that, what is the plasma frequency? Plasma frequency is a very important parameter, okay? So it is the electron density, because you have any atoms, each atom has z electrons. They have the electron density equals to n times z. So the plasma frequency of any material is the electron. You calculate the electron density. All electrons in the atoms, you know, which is as if they were free, okay? Why free? Because there's no restoring force. These are free electrons then, right? No free. The restoring force doesn't make any effect. The material behaves as if all electrons were freely moving in response to the applied frequency at frequency omega. So all electrons are freely moving, you know. And the material simply is transparent to the passage of the electromagnetic radiation. And the density that appears in the plasma frequency formula is the electron density. Calculate all the density, the entire density, which is n times z. So that's what happens. So what happens in this high frequency regime? We talk about dielectric. If we talk about the insulator, the result is only valid for omega larger than omega p, which we're talking about that. The medium behaves as a plasma, right? Our electrons behaves as if no, that's what it's saying, right? Very high frequency, no restoring force is present. And that's why materials are transparent to high frequency radiation, right? We don't have an absorption, little interaction, right? Because there's no restoring force, no resonance. Then you have just the electromagnetic wave just passes through the material. So X-rays is a good example, right? The other thing is important thing here, which I might mention in the next lecture, but people make X-ray wave. I mean, people make an optical fiber, right? Optical fiber have a core with a refractive index, which is the root square of the relative permittivity. Let's say the core and the cladding and core. And the end core is generally larger than end cladding. So you can guide an electromagnetic wave when you have, total internal reflection. By total internal reflection, you can guide a mode through the optical fiber, provided that you have end core larger than end cladding. You have guiding, right? When you go to X-rays, these are two pieces of glasses, different refractive index, and core larger than any cladding. When you go to X-rays, you have to do the opposite. You have to put air outside. In fact, you have to put, for instance, you have to make a capillary glass, right? So you put, that's what people do. People enhance the transmission of X-ray through capillary tubes. You put air, right, or vacuum, air, and some material, because n is smaller than 1, because epsilon relative is smaller than 1. So we can guide X-rays using capillary glass, empty glass in the middle, right? The nice thing about the electron harmonic oscillator model is that it can also predict the behavior of conductive materials, right? To analyze the behavior of conductive materials, we assume that only free electrons are present in the model. So what does it mean? It means that we don't have restoring forces. Okay, let's now forget about the different charges, many charges. Let's just consider now the general feature. So if you have only free electrons, set the resonance frequency. Let's say that you have only one type of charge. Okay. Of course, we can add to this model, we can add the permittivity function of the background system of the bound electrons and the bound nuclei and the nuclei. You can add that. That's going to be an additive effect. But let's look only into those elements that are free electrons. So now we have the density, right? Let's go to density. In time domain, the curly J equals to the density of charge density times the velocity, as we defined before. So if you calculate the phase of J, it's going to be J omega, which is the derivative, right? NQX. So it's just a matter of determining J and relating J to E, we get the conductivity function. So if you calculate, that can be calculated because we already calculated X. Remember that we had omega square, omega 0 square minus omega square, but omega 0 is 0, right? So that's what we have. There's a frequency function. So that's the conductivity. Here there's a missing E here. Right? So NQ square, you see NQ times Q is NQ square over M. So have an omega here. Omega square becomes omega, and this omega cancels out this one. So that's the response, right? If you go to the omega equals 0, we have the DC regime, right? That's what we did before. So that's the function. If you divide by J here, it's going to be gamma. If I multiply by minus J on numerator and denominator, that's what we get, this response. So this is a complex conductivity. That's how it would be, in fact. But in the DC regime, omega equals 0, then we have this relationship here. And gamma, if we replace gamma, if we compare that with the model that we developed earlier, when we talk about conductivity, that's the conductivity we got. We had the collision time, which is equal to 1 over gamma, right? So that's the conductivity. That's what we get. Right? That's what we obtained previously. We can also look into the imaginary part of the permittivity, and for instance, you can model conductivity by looking into the imaginary part of the permittivity. Let's see that how that is done. Okay, go to the Ampere's law, differential form. Curl of H equals to is already in the phasor regime. J plus J omega epsilon E. So that's an effective permittivity, I can say that. I can put J equals sigma E, right? Right? J equals sigma E. So it's going to be sigma plus J omega epsilon. So I can call this a J omega epsilon effective, to write it down like this, as if the material didn't have conductivity. You can attribute all the transport properties to this effective permittivity here. So if we determine what is the effective permittivity, it's going to be epsilon divided by J omega, and sigma divided by J omega is minus J sigma over omega. So if the material has a conductivity sigma, it's the same as if it had a relative permittivity imaginary part epsilon 2 prime, right? So it means that epsilon 2 prime, a material that has a conductivity sigma, is equivalent to a material having a imaginary part of the relative permittivity equals to sigma divided by omega epsilon 0, right? So either you can say, well, this material is a conductor, is as if it had this relative permittivity imaginary part. Or, on the other hand, well, this material has a relative imaginary permittivity. It has an equivalent conductivity given by omega epsilon 2 prime epsilon 0. Okay? So if you go to a model and we determine this imaginary part of epsilon, we just multiply by omega epsilon 0, we get the conductivity. Let's look how it is. Let's look into our model again, okay? That's the behavior that we get for a single charge, okay? If we assume omega 0 equals 0, what happens? Well, let's see. That's the function we get. When the frequency is very small, this term is going to be larger than this one. Because this is linear with omega, this is square, goes with the square of omega. So for omega very close to 0, this dominates. So the response is going to be something like this, right? So we can work this out. So it's going to be 1 minus J something. This something is the imaginary part of the relative permittivity. Then use that formula. Omega epsilon 0 epsilon 2 prime is the conductivity. Then you have again the same result that we had before. Okay. Let me just make a quick comment here that for high frequency, let me go back. Let's look at this formula here. Okay. Let's look at that. Let's look into metals at high frequency. I didn't talk about that. Talk about high frequency in general, right? Now I'm going to talk about metals. Metals have no resonance. The response is something like this, right? So let's say each atom releases 1 electron only, okay? So that's what we have. So when this omega much larger than gamma, so omega square much larger than omega gamma, what we have? The relative permittivity is real, right? It's going to be real, which equals to 1 minus nq square divided by m epsilon 0 omega square. This is the plasma frequency. Again, here n is the electron density because we are talking about free electrons only. So the permittivity is like this, that formula that we derived before. Now, this is valid. There's no resonance, right? This is valid for any frequency. And this function here might be positive or negative, right? So that's the behavior of metals. If you look in metals at high frequency, it's as if it had a relative permittivity given by this function. And if you look at this function, it crosses for omega equals omega p equals plasma frequency, which is very high. The permittivity equals to 0. For omega going to infinity, it goes to 1, right? And for omega is smaller than omega p, this goes negative. And that's what it is. A metal, if you look into the permittivity of a metal, this is epsilon prime, sorry. The permittivity of a metal has negative values for omega smaller than omega p. Right? So we can look into metals as having a permittivity which is negative below the plasma frequency. For most metals, the plasma frequency is in the ultraviolet, in the blue region. You know, different materials have different plasma frequency. So they become transparent when your frequency is larger than the plasma frequency. And they block the wave. Every time the permittivity is negative, we can show that the wave is going to be blocked. We can talk about that in the next chapter. We're going to look into that next lecture. We're going to see that, okay? But I mean, when you go at a frequency larger than omega p, you have a block. You can transmit the wave through the metal. If you have a piece of microscope slides with a thin coating of gold, if you look through the light, okay, very thin coating, you're going to see green. So it means that the green component is passing, so you can see it. Okay. If you have a very thin silver film, on the other hand, if you look through the light, you're going to see blue. Okay. Only in the blue region you start seeing something crossing. So it means that the plasma frequency of silver is higher than that of gold. Gold has a lower plasma frequency. So because green has a frequency wavelength larger than the blue components, conversely, the plasma frequency for, green has a lower frequency than blue. Then you can see it. And aluminum is the same. Aluminum goes through the plasma frequency for aluminum. Each atom releases 3 electrons, in fact. Goes to ultraviolet. Okay. So when you see that, if you see a thin film of metal, try to look through the glass. Very thin film. You have in research laboratories, you have those. People who work with thin metal films, they can have those. You know, you see that gold is going to transmit green and silver blue. Okay. Okay. Let's go to our final part of the lecture today. So this is the response. We can explain metals and insulators, and generally the permeability function might have those bands, resonant bands, high interaction with the applied field, low interaction, high absorption, low absorption. So this is a general feature of those material parameters relative to the passage of electromagnetic waves. Let's look into the Poynting theorem, how it looks like when you now take into account the fact that for harmonic fields, the response depends on frequency and might have real and imaginary parts. Okay, so you might have insulators and conductors. Insulators may exhibit dielectric or magnetic damping losses, right? Damping constants is due to loss. As we showed before. And the permittivity function can be used, the function that we just derived using the harmonic oscillator model can be used to represent other properties like the permeability, right? So we are going to assume that the relative permittivity has this structure here, real part and imaginary part. We are talking about passive medium. All the media are passive. So we have a minus here, it means that epsilon 2 prime is positive. Same thing as the permeability. We are going to see that this sign has implication. The sign as a whole has to be negative to represent a loss. Okay, so for passive media, I have a conductivity, permittivity imaginary part, and permeability imaginary part as well, all positive. So recall that the Poynting theorem in the harmonic regime has this flux, the power flow inwards a closed surface equals to this component, which is the exchange of energy between field and free carriers, right? And a difference between energies, magnetic and electric, minus J2 omega. And the energy densities are those ED conjugate, BH conjugates. And these are complex numbers, recall that, right? Because recall that D and E, they are related by a complex permittivity parameter, B and H by a complex permeability parameter. So when we do the calculation, I'm not going to do that algebra, it's very simple to do it. You can show that the active power, so the real part, okay, just calculate the real part, means the active power that flows inwards the volume. That's going to be given by this term here, which has an effective conductivity, I'm going to talk about that soon, plus a term that has the imaginary permittivity. You see that this is positive here. So it means that mu 2 prime is positive. So that's magnetic losses. This one has conductive and dielectric losses. Why? Because, well, the conductivity effectively is sigma plus that contribution due to the dielectric losses, which is equivalent to an effective conductivity added to the already existing conductivity, okay? So that's what we get. So it shows why you have those imaginary parts always positive, right? The imaginary part of the power that flows inwards is called the reactive power, right? And this has to do, has a minus here, right? WE minus WM. So that's you see that the energy has to do with the real part of the permittivity and permeability. And you always have a difference. It means that you can determine if a system is more capacitive or more inductive. If it has more electrical energy than magnetic energy. If the system has more electrical energy stored than magnetic energy, it means that this number is positive, so the imaginary part is going to be negative here. So you're going to have a capacitive system, right? If you have WE smaller than WM, you're going to have an inductive system. It means that there's more magnetic energy stored than electric. You can see that by looking into a secret, model. VI conjugate gives the power. If you look into a capacitor, right? I equals J omega C V. VI conjugate is the power, complex power. It's proportional to complex power. It's going to be I conjugate is minus J, right? So you're going to have a power which is negative, complex, the imaginary part of the complex power is a negative imaginary number, so it means that this is a capacitive power, right? So it means that the power is negative as shown here. WE larger than WM, negative. On the other hand, if it's inductor, V equals J omega Li, right? And Vi conjugate is going to be positive imaginary part, which means Wm larger than We, so makes sense. Okay? Well, I just have some special case. If you don't have, if your medium is lossless, no losses, no conductivity, no real imaginary part of permittivity or of the permeability, so it means that the real part of the power flow inwards, this is zero, it's going to be zero, of course, right? So there's no loss. What enters leaves the volume. So have only reactive power, okay? If you only have conductive losses and no dielectric or magnetic losses, then you're going to have only that term due to Ohm's law, right? So you're going to have that, and the energy is going to be entirely real, right? You don't have any complex number here. This We and Wm are real. So in general, you have that formula I already derived for you previously, right? That's the power density. So in summary, this lecture is useful for showing you how materials respond to the application of harmonic field, right? There are regions that have high interaction, which are those resonating regions, and regions in which the interaction is very weak, and the electromagnetic radiation just passes through the material without any effect. Okay, so I think we're gonna stay. Gonna close here, and we expect to see you in the last lecture next week. Until then, bye bye.